66 million years ago, an asteroid 12 kilometers wide ended 3/4 of all life on Earth, and not one species saw it coming. Subscribe if you want more of the cosmos. This is white space. Settle in. There is something in us that refuses to stay still. Long before we had the tools to reach past our own atmosphere, we were already looking up, measuring the distances between stars, calculating orbits, imagining what might wait on the other side of the dark. That impulse is older than science. It may be older than language. And in every era of human history, it has pushed us further than we thought possible.
2 centuries ago, crossing an ocean meant months of uncertainty, sickness, and the very real possibility of never returning. Today, we think nothing of flying between continents in hours. The question that now sits at the edge of our ambition is not whether we can reach other worlds, but whether we will survive long enough to do so. And if we do survive, what will we become? These are not questions for the far future. The decisions being made right now, in engineering labs and space agency boardrooms and university physics departments, will determine whether our species remains permanently confined to a single fragile planet or becomes something far larger. Let us follow that thread as far as it goes. The argument for leaving Earth is straightforward. Every civilization that has ever existed on this planet has eventually ended. Empires, cultures, species, all of them finite. Some were destroyed by conflict, others by disease, and many by events entirely beyond their control. 66 million years ago, an asteroid roughly 12 kilometers wide struck what is now the Yucatan Peninsula, and within a geological instant, 3/4 of all species on Earth were gone. The dinosaurs had no warning, they had no plan, they had nowhere else to go. We are different in exactly one way, we know it can happen again. The Chelyabinsk meteor that exploded over Russia in 2013 released energy equivalent to 30 times the Hiroshima bomb and injured over 1,000 people, and it arrived completely undetected. The Tunguska event in 1908 flattened 2,000 square kilometers of Siberian forest. These were small objects. The solar system contains thousands of bodies capable of causing extinction-level damage, and our tracking of them remains incomplete. But the asteroid threat is only one item on a long list. A supervolcano eruption, comparable to the Toba event 74,000 years ago, may have reduced the global human population to a few thousand individuals, a bottleneck so severe it nearly ended our lineage before it began. A pandemic of a sufficiently aggressive pathogen, a nuclear exchange between major powers, a runaway ecological collapse, the specific mechanism matters less than the principle. Any species that concentrates all of its members on a single world is making an enormous bet. Every day that passes without catastrophe is not evidence the bet is safe. It is simply evidence that we have been lucky so far. The rational response is to become multiplanetary, to establish at least one other place in the solar system where human life continues independently, so that no single catastrophe can end the story. Mars is the most obvious candidate. It is the nearest world with a solid surface, a day nearly identical in length to ours, and enough geological and chemical resources to potentially support a permanent human presence. It is not welcoming. Its atmosphere is 95% carbon dioxide. Its surface temperature averages -60 degrees Celsius, and it receives roughly twice the radiation dose that would be considered safe for a human worker over a career. But none of those obstacles are physically insurmountable. They are engineering problems. And human beings are very good at solving engineering problems when the incentive is strong enough to reach Mars with any regularity. However, we first have to solve the problem of getting off Earth cheaply. Right now, placing 1 kilogram of payload into low Earth orbit costs roughly $2,000 using the most efficient launch systems currently operational. That figure has dropped dramatically over the past decade.
Reusable rockets developed by private companies have compressed it by more than an order of magnitude compared to where it stood in the 1990s, but cheap enough for routine interplanetary travel requires another order of magnitude reduction. Several approaches exist. The most frequently discussed is the electromagnetic launch system, essentially a large linear accelerator embedded in a mountainside or hillside, capable of accelerating a vehicle to orbital velocity using electrical energy rather than chemical propellants. The concept has been studied for decades. A variant called the Star Tram proposal imagines a superconducting magnetic levitation track running up a mountain peak, launching payloads at velocities exceeding 8 km per second. The engineering challenges are formidable, but the physics are sound. A more ambitious concept is the space elevator. A cable extending from the equatorial surface up to a counterweight positioned beyond geostationary orbit, along which robotic climbers could carry cargo at a fraction of current launch costs. The fundamental obstacle has always been materials. No substance available in quantity could survive the tensile forces involved. Carbon nanotubes changed that calculation in theory. Fibers of aligned carbon atoms can achieve tensile strengths 50 times greater than high-grade steel at a fraction of the weight. Whether they can be manufactured at the scale and purity required remains an open question, but laboratories in Japan, China, and the United States are actively working toward it. These infrastructure investments would transform Earth orbit from an expensive frontier into something resembling a maritime harbor, a place where ships are assembled, fueled, and dispatched in quantity. And the first place most of those ships would be dispatched to is the Moon. The Moon is not a destination in itself. It is a waypoint, a construction site, and a laboratory. Its surface contains vast quantities of oxygen locked in mineral oxides, hydrogen ice in permanently shadowed craters near the South Pole, and regolith that can be processed into structural materials. The lunar surface also provides an environment where large spacecraft components could be manufactured and assembled in low gravity with no atmosphere to contend with. A lunar-based mass driver, the same electromagnetic catapult concept adapted for low-gravity conditions, could supply materials to orbital construction facilities at costs far lower than launching equivalent mass from Earth. Missions to the lunar surface are already being planned with permanent occupation as an explicit goal. The Gateway Station, positioned in a near rectilinear halo orbit around the Moon, is designed as a transit hub capable of supporting crews conducting both lunar surface operations and deep space missions. The timeline for permanent lunar habitation keeps shifting, but the direction of travel is consistent. The Moon is coming back into focus, not as a prestige destination, but as an industrial base. Between the Moon and Mars, however, lies the real technological gap. Chemical rockets, which burn oxygen and hydrogen or oxygen and methane to produce thrust, are approaching the limits of what physics allows them to achieve. The exhaust velocity of a chemical engine determines how efficiently it uses propellant, and the theoretical ceiling for that exhaust velocity in a chemical reaction is effectively reached. Getting from Earth orbit to Mars in a reasonable time frame using chemical propulsion requires carrying enormous quantities of propellant, which in turn requires enormous structural mass to contain it, which in turn requires even more propellant. The engineering becomes self-defeating at a certain scale. The way past this is nuclear propulsion. In a nuclear thermal rocket, a fission reactor heats a propellant, typically liquid hydrogen, to temperatures far beyond what any chemical reaction can achieve, and expels it through a nozzle. Because the energy comes from nuclear fission rather than combustion, the exhaust velocity can be 2 to 3 times higher than the best chemical engines. Less propellant is needed to achieve the same velocity change. A spacecraft that would take 9 months to reach Mars on a chemical trajectory. might make the journey in 4 to 5 months under nuclear thermal propulsion. That difference is not trivial. Every additional month in deep space is additional radiation exposure, additional bone density loss, additional psychological strain on the crew. Nuclear electric propulsion takes the concept further. Rather than heating propellant directly, a reactor generates electricity which powers an ion drive or similar electric thruster. The exhaust velocities achievable with electric propulsion are dramatically higher than any thermal system, which means extremely high propellant efficiency. The trade-off is thrust. Electric thrusters produce force measured in millinewtons rather than kilonewtons. A nuclear electric spacecraft accelerates slowly but continuously, gradually building velocity over weeks and months until it reaches speeds that no chemical rocket could match. For cargo missions without time constraints, nuclear electric is potentially transformative. For crewed missions, a combination of high-thrust nuclear thermal for departure burns and nuclear electric for cruise phases might offer the best balance. Russia's ZUS nuclear tug project, currently in development, proposes exactly such a hybrid architecture. A compact, fast neutron fission reactor running on uranium fuel would power a high-efficiency plasma thruster, with mission profiles extending to Jupiter and its moons. Independent American programs at companies like Ultra-Safe Nuclear Corporation and BWX Technologies are pursuing designs that could be tested in orbit before the end of this decade. The propulsion catalog does not end at nuclear fission. 7 distinct concepts deserve attention, each occupying a different position on the spectrum between current engineering reality and speculative physics. The first is a nuclear pulse drive, a concept that achieves high thrust, not through continuous reaction, but through a rapid sequence of small nuclear detonations behind a thick pusher plate. Project Orion, studied seriously at General Atomic in the late 1950s and early 1960s, produced calculations suggesting that a pulse drive spacecraft could reach Mars in weeks and approach Alpha Centauri in decades. The political obstacle was the Partial Test Ban Treaty of 1963, which prohibits nuclear detonations in space. The technical obstacles were always secondary. The physics remained valid. Project Daedalus, a follow-on study conducted by the British Interplanetary Society in the 1970s, refined the concept using deuterium helium-3 pellets ignited by electron beams rather than fission bombs, proposing a mission profile that could deliver an unmanned probe to Barnard's star 6 light-years away within 50 years of departure. The second concept is the microwave resonance cavity thruster, popularly called the M-Drive after its British inventor Roger Scheuer. The device is a truncated cone through which microwave radiation is reflected, allegedly producing thrust without expelling any propellant mass. Most physicists regard it with deep skepticism because thrust without expelled mass violates conservation of momentum as conventionally understood. However, multiple independent laboratory tests have reported small but measurable thrust figures, typically in the range of tens to hundreds of micronewtons, that cannot be fully explained by experimental artifact. NASA's EagleWorks laboratory published results in 2016 suggesting thrust of approximately 1.2 millinewtons per kilowatt. The effect, if real, remains without accepted theoretical explanation. Further experiments using highly sensitive torsion balances and optical interferometry are ongoing. The possibility cannot be dismissed, and if it is eventually confirmed, a solar-powered M-Drive could, in principle, continuously accelerate a probe without any propellant budget. The third concept is the electric solar wind sail proposed by Finnish scientist Pekka Janhunen in 2004. The sun does not only emit light, it continuously streams charged particles outward at speeds between 300 and 800 kilometers per second.
This solar wind is too tenuous to push a conventional sail made of physical film, but it can interact with an electrostatic field. A spacecraft deploying long, thin conducting tethers, maintained at a high positive voltage by a small onboard electron gun, would experience a repulsive force from the incoming proton flux. Simulations suggest that such a sail could reach the heliopause, the boundary of the Sun's magnetic influence, roughly 120 astronomical units from the Sun in roughly a decade. For comparison, the Voyager 1 probe, launched in 1977, did not reach the heliopause until 2012, 35 years after departure. The acceleration is modest but continuous, requiring no propellant and only enough electrical power to maintain the tether voltage. The fourth concept, ion propulsion, is not speculative at all. It is operational. Ion drives work by ionizing a propellant, usually xenon gas, and accelerating the resulting ions through an electric field to exhaust velocities 10 to 20 times higher than chemical rockets. The trade-off is thrust. Current ion engines produce roughly 100 millinewtons, about the force exerted by a piece of paper resting on a surface. But they operate continuously for years. The Dawn spacecraft, launched in 2007, used its ion drive to orbit both the asteroid Vesta and the dwarf planet Ceres, a feat impossible with chemical propulsion, which would have required far more propellant than the spacecraft could carry. The Hayabusa missions to asteroids Itokawa and Ryugu both relied on ion propulsion. Future developments aim at higher specific impulse and significantly greater thrust, potentially enabling direct Mars missions with much shorter transit times than current chemical trajectories. The fifth concept, plasma propulsion, amplifies ion drive principles by heating propellant to temperatures at which it transitions into a magnetically confined plasma state, tens of thousands to millions of degrees. The heated plasma is then expelled through a magnetic nozzle, producing thrust hundreds of times greater than a conventional ion drive, though still far below chemical rockets. The Vecimara engine, developed by former NASA astronaut Franklin Chang Diaz and his team at Ad Astra Rocket Company, has operated in ground tests for over 10,000 hours and could in principle cut the transit time to Mars from 6 to 9 months down to approximately 39 days, using megawatt-class electrical power levels achievable only with a large nuclear reactor. A ship of 100 tons under Vecimar propulsion, at projected efficiency levels, could reach velocities of thousands of kilometers per second given sufficient time and power. The sixth concept is thermonuclear fusion propulsion. Humanity has been attempting controlled nuclear fusion since the 1950s, and it has always remained just out of reach. But the physics are not in question. Fusing isotopes of hydrogen releases energy per unit of fuel mass that dwarfs fission, and the fuel, deuterium and helium-3, is effectively inexhaustible. A fusion rocket would use magnetically confined plasma at temperatures of hundreds of millions of degrees, channeled through a magnetic nozzle at exhaust velocities measured in thousands of kilometers per second. At 7% of the speed of light, a figure achievable in principle with deuterium-helium-3 fusion, a probe could reach the Alpha Centauri system in roughly 60 years. A crewed mission allowing deceleration at the destination would require higher performance still, but even at half that velocity, travel between nearby stars becomes a multi-generational engineering project rather than a physical impossibility. Private companies are now pursuing fusion energy on compressed timescales that would have seemed implausible a decade ago. Commonwealth Fusion Systems, TAE Technologies, and Hillian Energy have all secured substantial funding and published results suggesting commercial fusion power before 2025. Whether the transition from power plant to rocket engine follows quickly depends on engineering details not yet resolved, but the trajectory is visible.
The seventh and final concept sits at the edge of what physics permits.
A warp drive, as originally proposed by Mexican physicist Miguel Alcubierre in 1994, would not accelerate a spacecraft through space in the conventional sense. Instead, it would contract space in front of the vessel and expand it behind, so that the ship rides a wave of space-time distortion. Inside the bubble, the local physics remain normal. No relativistic time dilation, no inertial forces from acceleration. The ship could traverse interstellar distances in days without technically violating the cosmic speed limit. The energy requirements in Alcubierre's original formulation were impossible, equivalent to the mass energy of a planet the size of Jupiter, in exotic negative energy form. Later refinements by Harold White at NASA's Eagle Works laboratory reduced the theoretical energy requirement dramatically. And small experiments attempting to detect space-time distortion at the microscale are underway in specially isolated facilities where even seismic vibration is damped by pneumatic supports. Whether anything practical ever emerges from this remains genuinely uncertain, but the mathematics have not been proven impossible, and that alone makes it worth continued investigation. The ships that would eventually carry humans to other stars will need somewhere to dock, refuel, and return to. And before stars, they will need somewhere in this solar system, a habitat not on a planetary surface, but in the void between them. The idea of building permanent human communities in free space dates to the earliest decades of the space age. Konstantin Tsiolkovsky, the Russian schoolteacher who laid many of the mathematical foundations of rocket science, proposed rotating toroidal habitats, ring-shaped stations spinning on their axis to produce artificial gravity through centrifugal force. The concept was elaborated in architectural detail by Wernher von Braun in the 1952 Collier's magazine article that gave millions of readers their first image of a wheel-shaped space station, a design later immortalized in Stanley Kubrick's film. But the most rigorous technical development came from NASA-funded summer studies at Stanford University in the mid-1970s, which produced three distinct designs. The Stanford Torus proposed a ring nearly 2 kilometers in diameter, housing between 10 and 140,000 inhabitants. The ring would complete 1 revolution per minute, generating surface gravity approximately equal to Earth's at the inner rim. At the hub, which rotated slowly if at all, docking facilities would receive cargo and personnel from Earth. Solar mirrors mounted along the central axis would redirect sunlight into the interior of the ring, where it would illuminate a continuous curved landscape of fields, forests, and inhabited structures. The interior, as the designers conceived it, would not feel like a spacecraft. It would feel like a narrow valley wrapping around on itself, with a bright stripe of sky overhead. That was, in fact, the opposite side of the ring. The Bernal sphere took a different geometric approach. A hollow sphere, 500 meters in diameter, would rotate to provide gravity at its equatorial band, with the poles remaining in low gravity zones suitable for docking, zero-G manufacturing, and recreational use. The initial concept, called Island 1, was scaled for 1,000 inhabitants, a size chosen for practicality rather than ambition. Larger versions, Island 2 and Island 3, progressively increased the sphere's diameter and population capacity. The spherical geometry was specifically chosen to minimize surface area relative to enclosed volume, an advantage for radiation shielding, while providing enough interior space to sustain a closed ecological cycle. The O'Neill cylinder, named for physicist Gerard O'Neill, who championed all three designs, proposed twin cylinders, 8 kilometers in diameter and 32 kilometers long, counter-rotating to cancel angular momentum and simplify docking. Each cylinder would have alternating strips of transparent windows and opaque land panels. By adjusting the angle of external mirrors reflecting sunlight through the windows, The habitat could simulate a full day-night cycle. Agricultural rings attached to the exterior would exploit the full solar energy flux without competing with residential space. The population of a single O'Neill cylinder pair could reach several million. These designs were developed in enough engineering detail to produce credible cost estimates. At mid-1970s prices, the Stanford Torus was projected at approximately $200 billion, expensive but not obviously more so than the Apollo program scaled over a comparable time frame. The material supply problem was addressed through lunar mining, extracting raw material from the moon using electromagnetic catapults and processing it in orbital factories. Helium-3, rare on Earth but present in the lunar regolith from billions of years of solar wind exposure, could supply a fusion economy. Silicon, aluminum, iron, and oxygen are abundant in lunar soil. The Earth itself would only need to supply refined components and biological material. The Dyson sphere represents the ultimate endpoint of this logic, a structure enclosing an entire star, capturing its total luminous output rather than the fraction that happens to strike a planet. Freeman Dyson, the British-American physicist who described the concept in a 1960 science paper, proposed it not as an engineering blueprint, but as an observational target. A civilization that had exhausted its planet's resources might build such a structure, and it would be detectable by the infrared signature of waste heat radiating from its outer surface. Searches for such signatures have been conducted in astronomical survey data, most extensively by the Glimpsing Heat from Alien Technologies project analyzing data from NASA's WISE infrared telescope. No confirmed Dyson sphere has been identified, though several anomalous infrared excess sources remain unexplained. The fundamental instability problem, a rigid sphere surrounding a star, is dynamically unstable and would drift until it contacted the star, is typically addressed by replacing the sphere with a swarm of independent solar collectors in coordinated orbits. The practical engineering remains in the domain of a civilization millennia beyond our own, but the physics imposes no absolute prohibition. If some of those future inhabitants of these orbital cities are the colonists of Mars, they will over centuries become something noticeably different from their Earth-born ancestors. The question of how the human body would change under Martian conditions is not merely speculative. We have substantial evidence from physiology, genetics, and the observed biological responses of humans in extreme environments. Martian surface gravity is approximately 0.38 times Earth's. A person massing 100 kilograms would weigh 38 on Mars. Within 2 or 3 generations of full-time residents, the skeletal architecture of Martian-born humans would begin to shift. Bones that carry less compressive load grow differently, less dense in certain directions, potentially more elongated in others. We observe this process in the microgravity of the International Space Station, where extended missions produce measurable bone density loss and muscle atrophy. On Mars, with some gravity but significantly less than Earth's, the long-term developmental outcome would be distinct. Researchers at the University of Washington Center for Space Medicine have modeled scenarios in which Martian humans develop lighter, longer skeletal frames over 10 to 15 generations, bodies optimized for their world's gravitational regime rather than ours. Close quarters living is unavoidable in the early phases of Martian colonization. The surface radiation environment requires that habitats be either buried or heavily shielded. This means lower ceilings, compact corridors, and limited natural illumination. Conditions that parallel those associated with elevated rates of myopia in children who spend most of their time indoors. Studies in Singapore and Hong Kong, where indoor living styles have driven extraordinary rates of myopia among school-aged children, provide a striking precedent. Martian-born humans may well develop significantly reduced distance acuity within just a few generations, not because the trait is directly selected for, but because the developmental environment consistently promotes it. The radiation environment is the most dramatic pressure on Martian biology. Mars has no global magnetic field comparable to Earth's, its atmosphere. At roughly 1% of Earth's surface pressure provides minimal absorption. Surface radiation on Mars is approximately 2 millisieverts per day, far above the annual occupational limit for radiation workers on Earth, and several orders of magnitude above background levels in a well-shielded building. Over the decades-long timescales needed for a permanent colony, this creates an intense selection pressure for radiation resistance. Mutations will occur at elevated rates. Most will be harmful. Those that confer any protective advantage will propagate preferentially through the population. The biochemistry of UV and ionizing radiation protection varies across life on Earth. Organisms like Deinococcus radiodurans can survive doses thousands of times lethal for humans, using novel DNA repair mechanisms and pigment chemistry that we do not possess. Martian humans would not evolve toward Deinococcus in 300 years, but the direction of selection pressure is clear: resistance to oxidative and ionizing damage, novel pigmentation, perhaps enhanced cellular repair pathways. The oxygen supply in Martian habitats will be manufactured, maintained at lower partial pressures than Earth's sea level atmosphere. Human populations living at high altitude on Earth, the Tibetan Plateau, the Andean Altiplano, have undergone documented genetic adaptations over 15,000 years of high-altitude residence. Tibetans carry variants in the IPAS1 gene, sometimes called the superathlete gene, that regulate hemoglobin production in ways that improve oxygen delivery efficiency at altitude. Similar adaptations in Andean populations affect different genes but achieve comparable results. Martian colonists living in maintained low-oxygen environments from birth would over centuries show analogous genetic drift, not by planned genetic engineering, but by the same selective mechanism that shaped Tibetans. The immunological trajectory on Mars is equally interesting. In a carefully controlled habitat environment, many of the pathogens that have driven human immune evolution simply would not be present. Childhood diseases, common bacterial infections, parasitic organisms, their introduction would be strictly controlled. In the absence of immune challenge, immune systems change. This can manifest as increased autoimmune activity, as seen in populations transitioning rapidly from high pathogen to low pathogen environments. Alternatively, specific immune capabilities may be progressively relaxed over generations where they are never tested, a kind of evolutionary budgeting. Martian humans might gain extraordinary resistance to the specific radiation and oxidative challenges of their environment, while becoming increasingly vulnerable to pathogens endemic to Earth, a divergence that would make visits between the two planets medically complicated in both directions. The behavioral and psychological substrate of the initial colonist population is worth noting separately. The people who choose to leave Earth permanently for Mars, who are willing to accept years of transit, decades of confinement, the near certainty of never returning, and the statistical likelihood of a shorter lifespan, are not a random sample of humanity. They will be selected for risk tolerance, adaptability, high extraversion, or high conscientiousness, depending on which traits their specific mission role rewards, and possibly for reduced separation anxiety. The earliest Martian generations will inherit not just their parents' genes, but their parents' psychology. And that psychology was selected by the self-selection process of who chose to go. Within 5 or 6 generations, that founding effect may be visible in the population's average temperament as clearly as in its average height. 300 years is a geologically trivial interval. In geological terms, 300 years leaves almost no record, a thin chemical layer at most, too fine-grained to reliably identify without knowing exactly where to look. And that observation opens a question that is simultaneously strange and serious.
Earth has existed for approximately 4.5 billion years. Complex animals have existed for roughly 600 million years. The genus Homo has been present for perhaps 3 million years.
Anatomically modern humans appeared approximately 300,000 years ago. Our industrial civilization, defined by fossil fuel combustion and global-scale technological infrastructure, is roughly 3 centuries old. In those 3 centuries, we have altered the chemical composition of the atmosphere, distributed synthetic compounds to every corner of the planet, and left a geochemical signature in sediment cores that will be detectable millions of years from now. The question is whether any other lineage across the 4 billion year history of multicellular life on Earth could have done something similar, and whether we would recognize the evidence today. Astrobotanist Adam Frank and his collaborator Gavin Schmidt explored this question in a 2019 paper in the International Journal of Astrobiology, which they called the Silurian Hypothesis, after the fictional reptilian aliens of Doctor Who predated humanity on Earth. Their examination was not a claim that prior industrial civilizations existed. It was an inquiry into whether we could detect one if it had. Their conclusion was sobering. The geological record preserves evidence of large-scale events primarily through their global chemical and isotopic signatures. Local structures, buildings, roads, mines are destroyed by erosion and tectonic recycling on timescales of millions of years. But sustained combustion of carbon-rich materials, large-scale mineral extraction, and persistent synthetic chemistry leave traces in carbon isotope ratios, nitrogen cycling patterns, and rare element concentrations that could survive as anomalies in ancient rock strata. There is already an example in the geological record of an event that looks, in certain ways, like what we would expect from an industrial pulse. The Paleocene-Eocene thermal maximum, occurring approximately 55 million years ago, involved a rapid injection of carbon into the atmosphere over a period of perhaps 20,000 years, rapid in geological terms, which means it could have been as short as a few centuries. Global temperatures rose by 5 to 8 degrees Celsius. Ocean chemistry changed dramatically. Thousands of deep-sea species went extinct. The carbon isotope ratios shifted in exactly the way we would expect from a rapid release of stored carbon. The cause remains debated: volcanogenic release, methane, clutterate destabilization, or some combination. But the signature is present and anomalous. Could a biological lineage have briefly achieved industrial capacity 60 million years before Homo sapiens and then vanished, leaving only this geochemical whisper? Probably not. The evidence points toward natural causes, and no vertebrate lineage of that period had the neurological infrastructure for technology. But the exercise reveals something important. If a civilization comparable to ours had existed 50 million years ago and collapsed, we might have only trace isotopic anomalies to find. The structures, the artifacts, the cultural records, all gone. The land masses on which they stood have been subducted, uplifted into mountain ranges, or eroded into sediment. This places our own civilization in a different perspective. We are not the end of history, and we are not necessarily the beginning of intelligence on Earth. We are one episode in a story that stretches across timescales our minds cannot intuitively grasp. The rocks of the Pilbara region in northwestern Australia contain recognizable microbial structures more than 3.5 billion years old, stromatolites, built by photosynthetic bacteria before animals existed, before plants existed, before the oxygen in our atmosphere had reached its current concentration. Those structures survived for 3.5 billion years, not because the organisms that made them were precious or protected, but because the local geology happened to be stable enough. What survives is not what was most important. It is what happened to end up in the right rock at the right depth.
Frank's paper suggests that the most durable evidence of any prior industrial civilization would be the same kind of evidence we are currently producing: isotopic anomalies in carbon, nitrogen, and oxygen, elevated concentrations of platinum group metals from catalytic processes, microplastic analogues from any petroleum chemistry-like technology, and spatial disruptions of soil and sediment patterns from large-scale excavation. These would be subtle, globally distributed, and easily misread as natural events, unless a researcher specifically knew what pattern to look for. We would not find their cities, we might find their chemistry. This has practical implications for the search for life beyond Earth. If we are looking for evidence of ancient civilizations on Mars, which may have had liquid water and potentially habitable conditions for the first billion years of its history, we should be looking not for ruins but for geochemical anomalies in ancient sedimentary sequences. The Mars 2020 Perseverance rover is currently caching samples from the Jezero crater, an ancient lakebed approximately 3.5 billion years old. Those samples, if eventually returned to Earth, will be subjected to the most sensitive chemical analysis ever applied to extraterrestrial material. Whether they contain biosignatures from microbial life is the primary question. Whether they contain anything stranger has not been the primary focus, but the tools to ask the question will be present. Venus, whose surface temperature currently exceeds 450 degrees Celsius due to an extreme greenhouse effect, may have been habitable for the first 2 billion years of its history before a runaway warming event transformed it into its current state. Whether that warming was entirely natural or, in the most speculative interpretation, influenced by whatever biological or industrial activity may have been present, cannot currently be determined. The surface of Venus is geologically young, resurfaced by volcanic activity within the last few 100 million years. The record of its early history has been largely overwritten. These are the kinds of questions that emerge when you sit with the Silurian hypothesis long enough, not as a literal claim about ancient civilizations, but as a methodological challenge. We have not been looking at the geological record for the signatures of intelligence because we assumed no intelligence existed before us. That assumption may be safe, but it has never been rigorously tested. Meanwhile, we can look outward and ask the same question at interstellar scale. If industrial civilizations form, persist, and produce detectable signatures, why do we not see those signatures throughout the galaxy? The answer depends heavily on which stage of development those civilizations reach. Soviet radioastronomer Nikolai Kardashev proposed in 1946 our classification system for civilizations based on their energy consumption, a scale that has since been expanded from 3 levels to 6. A type left civilization controls and uses all the energy available on its home planet, including all of the sunlight falling on it and all stored geological energy. It manages its weather, its plate tectonics to some degree, its global ecology. It is not a passive inhabitant of its world, but an active manager of a planetary system. Earth is not yet a type I civilization. We currently harness perhaps a few tenths of a % of the total solar energy reaching our surface, and we have no ability to control seismic events, modify storm systems at will, or redirect ocean currents on demand. Estimates based on current energy growth rates suggest we would reach Type 1 status within roughly 1,000 years, assuming we do not destroy ourselves in the process. The transition through Type I appears to be one of the most dangerous periods a civilization can face. At this stage, the civilization has enough power to alter its environment catastrophically, but perhaps not enough wisdom or coordination to prevent the most destructive applications of that power. Climate change, nuclear arsenals, engineered pathogens, unaligned artificial intelligence, each of these is a potential transition failure mode. The filter, if there is one, may be located precisely here. A Type 2 civilization has moved beyond planetary constraints. It taps the full energy output of its star.
approximately 400 billion megawatts in the case of a Sun-like star, using structures like the Dyson sphere or its variants, managing the orbits of every body in its system, potentially controlling stellar evolution itself. At Type 2, the civilization has solved the energy problem permanently. It is effectively immune to planetary catastrophe. It has the surplus to explore and colonize the nearby stellar neighborhood. A Type 3 civilization operates at galactic scale, controlling the energy of hundreds of billions of stars, potentially migrating stellar systems, engineering the structure of the galaxy itself over millions of years. At this scale, the civilization is essentially coextensive with the galaxy. Its signature would be in principle astronomically detectable anomalous infrared emission, unusual stellar dynamics, megastructures visible in survey data. Type 5 civilizations extend their reach across galactic superclusters, accessing the energy of structures billions of light years across. Type V civilizations interact with the full energy budget of the observable universe, potentially including processes at the boundaries between normal matter and whatever lies beyond the cosmological horizon. Type Vis-I civilizations, if the extension of the scale is taken to its logical conclusion, are capable of operating outside the constraints of a single universe, manipulating the fundamental parameters of physical law, creating or destroying space-time itself. At this level, the distinction between a civilization and what many religious traditions would call a deity becomes, at minimum, philosophically interesting. The gap between Type I and Type VI is not primarily a gap in technology. It is a gap in time. Every civilization that survives its Type I transition and reaches Type II has presumably been operating and growing for thousands of years. A civilization that reaches Type III has been doing so for millions. By the time a civilization reaches Type VAC, it has existed for longer than the current age of the universe. The scale is not a ranking of how clever a species is. It is a ranking of how long they have been alive and what the time has allowed them to accumulate. Given these scales, the silence of the cosmos becomes deeply strange. Our galaxy has been forming stars for 10 billion years. Earth is approximately halfway through the Sun's expected lifespan. If civilizations commonly arise and persist, there has been time for hundreds of thousands of them to reach Type II or beyond. Why is there no evidence? This is the Fermi paradox, named for the Italian-American physicist Enrico Fermi, who at Los Alamos in 1950 over a lunch conversation asked a question that has never been satisfactorily answered. Where is everybody? The proposed resolutions form a wide spectrum. The universe may be lifeless except for us. Life is so improbable that despite billions of planets, it has happened only once. Or intelligence may be common but technological civilization rare. Consciousness may arrive at many species, but the specific cognitive and social prerequisites for scientific inquiry and engineering may be extremely unusual. Or civilizations may be common but short-lived. They routinely develop the capacity for self-destruction before they develop the wisdom to avoid it, and the universe is therefore populated by the ruins of countless failed civilizations. Distance is a partial explanation regardless of which other factors apply. The observable universe is approximately 93 billion light-years in diameter. Our own galaxy, the Milky Way, is roughly 100,000 light-years across. A signal sent from the nearest star system, Alpha Centauri, takes 4.3 years to arrive. A signal from the far side of the galaxy would take 100,000 years. By the time a response could travel back to its origin, the civilization that sent the original message could have collapsed or been transformed beyond recognition. The detection problem is compounded by the fact that we have been listening for only a few decades, using instruments sensitive primarily to narrowband radio signals of the type we ourselves would produce with 1960s technology. A civilization that has been broadcasting for 1 million years may have moved to communication methods we have not imagined. Neutrino communications, gravitational wave modulation,
or quantum entanglement protocols that leave no electromagnetic signature.
We would not be missing their signal because the signal is weak. We would be missing it because we do not know what format to look for. There is also the possibility of intentional concealment. A civilization that has observed the trajectories of other species, including perhaps the aftermath of those species making contact, might decide that silence is the optimal strategy. The dark forest theory, developed in speculative science and science fiction, proposes that the universe is occupied by many civilizations, none of which announces itself, because any civilization that thus risks being targeted by another that views it as competition for finite resources. The silence would then be a collective behavior of fear rather than an absence of inhabitants. The great filter theory proposed by economist Robin Hanson offers perhaps the most uncomfortable framing. The combination of the apparently empty universe and the apparent difficulty of the various steps toward a technological civilization suggests that somewhere in the developmental sequence, the origin of life, the emergence of eukaryotic cells, the development of sexual reproduction, the emergence of intelligence, the development of technology, the transition through type I, there is a step that almost never succeeds, the great filter. If the filter lies ahead of us, the silence of the cosmos is a warning. If it lies behind us, if we have already passed the hardest step, then we are among the most sophisticated things in the universe. And the silence is not an absence, but a gift. Some version of humanity may eventually leave the solar system entirely. Not on rockets and not within a single lifetime. On ships designed not to reach the destination within the crew's lives, but to carry the civilization of the ship itself to a destination that only the descendants of the departure generation will see. The generation ship concept, sometimes called a world ship or interstellar arc, appears first in serious literature in Don Wilcox's 1940 story, The Voyage That Lasted 600 Years, which introduced the scenario of successive generations born, living and dying aboard a spacecraft moving between stars. Robert Heinlein's Orphans of the Sky went further, imagining a ship whose inhabitants have so thoroughly forgotten their situation that they believe the ship to be the entire universe, a parable of institutional memory loss and the danger of knowledge untethered from its context. The scenario demands taking the phrase living ecosystem seriously. A generation ship cannot be a spacecraft that happens to have people on it. It must be a world that happens to be moving. The ecological closure requirements are extreme. All oxygen must be regenerated biologically. All nutrients must be cycled through living systems. All waste must be converted back into productivity. Any leakage from the cycle, any accumulation of compounds that the system cannot process, eventually terminates the mission. The biological redundancy requirements for the founding population are equally specific. Genetic diversity must be sufficient to prevent the accumulation of deleterious recessive mutations over dozens of generations of limited gene pool. A duality when odd, study by Cameron Smith at Portland State University modeled the minimum founding population needed for a successful multi-generational interstellar mission and concluded that 49 mating pairs, approximately 98 individuals selected for maximum genetic diversity, represent a minimum threshold for long-term viability. The calculation assumed a journey of several hundred years and accounted for expected mortality from radiation exposure, accident and disease at rates higher than Earth baseline. Below about 32 individuals, the algorithm found no viable outcome regardless of other mission parameters. Cryogenic hibernation is sometimes proposed as a solution to the population problem. Reduce the active population to a handful of caretakers and keep the rest in suspended animation.
The practical difficulty is that nothing in current medicine can safely suspend human metabolism for more than a few hours.
The US Army's Emergency Preservation and Resuscitation Research Program is exploring induced suspended animation for trauma patients using hypothermia, achieving safe delays of hours to a day. Scaling this to years or decades faces biochemical obstacles that remain fundamentally unsolved. Ice crystals rupture cell membranes, metabolic byproducts accumulate even at low temperatures. The nervous system's protein structures are especially vulnerable to extended cold storage. Without a technological breakthrough in this specific domain, possibly involving new antifreeze biochemistry inspired by organisms like the tardigrade or the wood frog, generation ships would need full active crews. Feeding those crews over a multi-century journey requires a permanently productive agricultural system in a closed volume. Aeroponic cultivation, growing plants with their roots suspended in air and misted with nutrient solution, achieves far higher crop yields per unit area than soil-based agriculture, with no requirement for topsoil and sharply reduced water usage. Modern aeroponic systems can produce some crops at 80 times the density of field agriculture. Combining aeroponic food production with insect protein farming and algae cultivation. A 2017 analysis at the UK Centre for Ecology and Hydrology estimated that a sustainable food supply for 500 adults could be maintained in a pressurized volume roughly equivalent to half a square kilometre of floor area, demanding but not impossibly so, for a structure the size of an O'Neill cylinder. The psychological challenges of multi-generational confinement are harder to engineer around. The founding generation chose to go. The first generation born aboard the ship did not choose. By the third generation, the ship is simply where life happens, the only world anyone has ever known. Heinlein's characters who forgot they were on a ship represent an extreme but directionally plausible outcome. Managing institutional memory, preserving the mission's purpose across generations that have no personal connection to Earth or to the destination requires cultural engineering of a kind we have never attempted. The political and social structures that would emerge over centuries on an isolated ship with a fixed population ceiling would be unlike anything in our historical experience. The destination might be a star like Tau Ceti, approximately 12 light years away, and spectroscopically similar to our Sun. Tau Ceti hosts at least 4 confirmed planets, with at least 2 in the general vicinity of the liquid water habitable zone, though both are significantly larger than Earth. At a cruise speed of 1% of the speed of light, achievable in principle with advanced fusion propulsion, the transit time would be approximately 1200 years. At 10% of light speed, a century and a fifth. The difference between these scenarios is not merely a matter of engineering advancement. It is the difference between a mission spanning 40 generations and a mission spanning 2. Whether any version of humanity boards such a ship, the universe itself has a timeline that dwarfs all of these concerns by a factor that strains comprehension. The stars will not always shine. The laws of physics impose an end even on stellar evolution. The current universe is approximately 13.8 billion years old. It is in what cosmologists call the stelliferous era, the age of stars. Stars form from collapsing molecular clouds, burn their hydrogen and helium fuel over lifespans, ranging from a few million years for massive blue giants to several trillion years for small red dwarfs, and then die in ways determined by their mass. White dwarfs, neutron stars, black holes. The most massive stars are already old. Many have already died. The Sun has roughly 5 billion years of hydrogen fusion remaining before it expands into a red giant and eventually ejects its outer layers as a planetary nebula, leaving a cooling white dwarf. Within perhaps a billion years, increasing solar luminosity will push the inner edge of the habitable zone past Earth's orbit, rendering the surface uninhabitable regardless of human influence. But the universe will continue. Red dwarf stars, The most common stellar type will shine for trillions of years. The star Proxima Centauri, nearest neighbor to our Sun, has a mass roughly 1/8 of the Sun's and a projected lifespan of approximately 4 trillion years. In the deep future, the remaining stars will be overwhelmingly these small, dim, cool objects, barely visible, without optical aid, orbited by planets that receive enough warmth to be habitable, surrounded by skies almost entirely empty of other stars, because the galaxy will have expanded so dramatically. Eventually, over timescales measured in quadrillions of years, even these will exhaust their hydrogen. Star formation will slow to a trickle and then stop. The last stars to form, drawing on gas reservoirs depleted by 1 trillion years of prior star formation, will live out their final lives surrounded by a galaxy that is mostly dark. The stelliferous era ends somewhere around 100 quintillion years, a number followed by 20 zeros years from now. What remains after the last star dies is a universe of degenerate objects. White dwarfs slowly radiating their thermal energy away over unimaginable timescales, neutron stars rotating alone in the dark, and black holes. The era of degenerate objects is theoretically limited by proton decay. If the proton is unstable with a half-life consistent with certain grand unified theory models, the material in white dwarfs and neutron stars dissolves over roughly 10 to the power of 40 years. Releasing the energy of their constituent particles in a slow radiation that leaves nothing but a low-density gas of positrons, neutrinos, and photons. The black holes last longest. The most massive black holes, those at the centers of major galaxies carrying hundreds of billions of solar masses, evaporate via Hawking radiation over timescales of approximately 10 to the power of 100 years. After that, the universe contains no remaining concentrations of organized matter, no structures, no temperature differential sufficient to drive thermodynamic work, no gradient capable of sustaining information processing. This is the heat death, the maximum entropy state, the final equilibrium. Whether that final state is truly final, or whether vacuum fluctuations in a sufficiently old and empty universe can spontaneously nucleate new regions of organized complexity, is a question for physics that does not yet have an answer. The Poincaré recurrence theorem in its cosmological application suggests that given infinite time, any finite quantum system returns arbitrarily close to any prior state. But the timescales involved, numbers so large, they have no everyday analog, make the practical relevance of this theoretical comfort essentially zero on any human meaningful timeline. What we can say with confidence is that the universe runs on a clock, and that clock has always been running. The stars that formed earliest in cosmic history are now dead. The civilizations that might have arisen around those early stars, 4 or 5 billion years before our Sun even existed, have had time to rise and fall entirely. The universe has been doing this for longer than our species has been doing almost anything. We are not late arrivals. We are not early. We are one more expression of what happens when a universe capable of producing complexity over enough time produces enough of it. Whether that expression propagates itself across stars, survives its own technological adolescence, reaches for the Kardashev scale, or quietly exhausts itself on a single warming planet, we cannot know yet. That depends on decisions being made now, in the next decades, in this generation, by people who are in some cases not yet born. The rocks remember what came before. The universe keeps the ledger. The question is what the next entry reads.